So, welcome to this lesson about modeling real life phenomena. And today we will look on quadratic models. So, I will show you the graphs to the quadratic models, how they look like. I will show you 4 examples where you can find them in the real life. And I will show you some very good terms that describes what we have to know and understand about quadratic models, some concepts about quadratic models. So you write this down together with me. If I'm talking too fast or write too fast, you just take a pause and you can start again when you're done. So, first of all, a quadratic models as an equation looks like this. Equation. Y is equal to ax squared plus bx plus c. This is a model. A quadratic model because it's x squared like this, x2. And in real life phenomena, we have different values for the constants a, b, and c. And the models tells us something about reality that we want to understand. And with the help of this model, we can do prediction, say what's will happening in the future, for instance. So let's look on 2 examples. First, we have projectile motion. Projectile motion and economy. I will show you that it could be described with the same equation actually. So I will draw a diagram like this and this. So we have the x-axis and y-axis. But in this case, when we talk about projectile motion, on the y-axis we have the height. And here we have the x direction. And this is a real-life phenomena when you are throwing something in the air or you're shooting with a rifle or a gun. Then the bullet from the rifle or the stone which you throw in the air will be airborne like this. And you realize this is typical second degrees equation that describe this motion. So you are throwing something in the air and the x-axis could, for instance, describe the ground. So the height is the height above the ground when you are throwing something. And of course, in maths, the graph continues forever down like this, but we are just interested in what's happening in the air like this, above the ground. It could also be a problem with economy, where you have the price on the x-axis for some goods that you are selling, and this is the revenue, the income you have from selling something. And you know, if you have a very low price, you will sell a lot of products, goods, but the revenue will be quite low because the price is quite small. But if the price is very high, then you will sell too few of the goods you are selling, and then the revenue will be low as well. If you have a very high price, you won't sell anything at all, so the revenue will be none. And somewhere in the middle here, you will have the best price. So you will sell quite many of them, and you will get some quite lots for every goods that you are selling. Therefore, the revenue will be the highest. And in the next video, I will show you examples on this. Okay, let's look on area and energy. Okay, we have the same diagram like this. Now, if we have the radius of a circle and the area of a circle on the y-axis like this, then the area of a circle will increase with the radius something like this. Because the area of a circle is described or is calculated with pi r2. You understand this formula from the area of a circle. And r now is our x in this case, and we square it. And then it looks like this. Now, if I draw the graph from it, I could draw it for negative values as well, so it goes up like this, like a typical second degrees function. But normally, when we talk about area, we're not interested in some negative radius. So therefore, we just look on it like this. Something very, or at least a little peculiar about this graph is that if you have a radius like this, then we will have an area that we can find on the y-axis or the area axis. It's A. Now, if you double the radius of this circle, so double the radius, so we have 2r here. Now, the area of the circle is not twice as big, it will become 4 times as big. That's something typical for second degrees equations or functions that's a quadratic models. It also works for kinetic energy. So we could have energy on this axis, and we could have speed on this axis. If you are taking your driving license right now, you might have heard that if you have a speed, there is a kinetic energy involved with that speed for the car. Now, if you double the speed, the kinetic energy of the car is not twice as big, it's 4 times bigger. Therefore, the accident and the energy involved in the accident is 4 times higher if you crash your car or hitting someone with your car in a double the speed. So, think of that when you're driving your car. Okay, let's look on this in general. So we already know that the equation for the quadratic model is like this. ax squared plus bx plus c. So we have 3 constants that describes this function. And depending on what value for a and b and c, it could have a maximum point like this or a minimum point like this one has. Okay, the graph. So let's draw a diagram. The y-axis and the x-axis like this. So it could be written like this. This is one example of a second degree graph. Looks like this. And the graph is called a parabola. Parabola. fancy name for the second degree graph. And it could have a maximum value or a minimum value, depending on how you choose your value for a. So if a is greater than 0, then we say that it has a maximum value. We not just say, it actually has. Like this, a maximum value. Some students say it looks like a sad mouth. So to remember it, we can write sad mouth like this. And in maths, we also say that this graph is concave. Concave down. Concave if you look at it from below. If you look at it up from upside, it's convex. But from down, it's concave. Concave down. So it's some words that describe this graph. If a, the constant, the coefficient before the x2 term, if that value is positive, greater than 0, then it is concave down. It looks like a sad mouth. It has a maximum value. So you find the maximum value here. Y max. You can't find any higher value than this value. It don't have a minimum value. It continues, goes down and down forever. Now, if a is smaller than 0, that means a has a negative value. Well, then it has a minimum value or a minimum point. So, for instance, you can draw the graph like this. So it has the minimum value. So y min, like this. And it also looks like a happy mouth. So let's write it down so we remember it. A happy mouth. And in maths we say it's concave up. If we look at it from above or up, then it's concave. So we always use the word concave, not convex. Convave, looking from downwards, and concave, looking from upwards. It's good to remember. What's typical for a second degrees graph like this also, that is, it has a symmetry line like this. So a symmetry line is a vertical line that cuts the graph into two pieces, two halves, and it's symmetric around this line. If you go to the right and to the left, the same thing is happening, and it falls down on both sides. So this line is called axis of symmetry. Axis of symmetry. Let's write it down. Axis of symmetry. And you know already that a vertical line like this has an equation. You can write it down. So it is x is equal to a constant. The constant for the x value that you find on the x-axis. Now, the value depends on the values for a, b. For a and b in this case. So x with index letters sym, X symmetry is negative b divided with 2a. So if you have the values for a and b, then we can find the symmetry line or the axis of symmetry. Now, we will find this line if we want to find the maximum value, because these x values can help us to calculate the maximum value. Because if we know this value, we can put it inside instead of x and calculate this maximum value or the minimum value. Because a graph with a minimum value also have a symmetry line that cuts the graph into two halves that's symmetric around this axis. Now, if you want to find this maximum or minimum, then you use this x value and put it instead of x. So you know y, the y value is a function of the x value. So I write it like this: y, the y value for the maximum or the minimum, depends on this x value. So minus b divided with 2a gives us this maximum or minimum value. Okay, two things left about these graphs, and that is the y-intercept of the graph. That is where it intersects the y-axis. In this case, as I have written it, it intersects it in origin, but that's not always the case. So let's write it down. The y-intercept. The y-intercept of the graph, where it intersects. Well, it is the c value. And that is the case because when it intersects the y-axis, then x is 0. And when x is 0 there and there. So you multiply with 0. Well, that is 0. And you multiply b with 0. That is also 0. So y is equals to 0 plus c. Y is equals to c. On the y-axis, the x value is 0. So the y-intercept is 0 and c, if you write it as a coordinate on the y-axis. And the last thing we have to know, not much place left here, but that is the x-intercept. The x-intercept. That is where it intersects with the x-axis. Here you can see the intercept. Here you can see it, and here you can see it as well. And that is when the y value is 0. Y, you see the axis here? It's 0 here, but it's also 0 all along the x-axis. And you know that when y is 0 here, and then you have a second degrees equation. 0 is equal to this. And you have already solved the equation like this. And then the x value depends on the constant a, b, and c with this formula. Minus b plus minus b squared minus 4ac and the square root of that. And then you divide it with 2a. And you have this formula in your formula booklet if you don't remember it. And in the next videos, I will show you how you use this formula and how we use this information to modeling real-life phenomena. Okay, thank you.